Alright guys, so today is going to be part 2 of the popping noises, and there's probably going to be a part 3. So here, I'm just going to break it down for you. So I basically, did the research and then understood it from an electrical engineering perspective. At least my degree will be good for this. Didn't help me find a job. So a lot of this stuff, like I said, I kind of knew the solution right away when I first heard it, and we're going to discuss that in the next video. So you basically have to open this up and then put some passive components in there, right? When you want to filter stuff like this out, popping noises, what you want to do is you want to put a capacitor in there, right? So I will talk about that later in the next because that's going to involve opening it up and everything, and then I'll have to buy I'll talk about this towards the end of this video about how I'll do that in the next video. Okay, all right, so what I've done is yesterday the pop returned, so it looks like it's happening when when you first turn it on. So it's been sitting on standby. Now I put a note on the last video where you have conflicting statements from Orange says, so watch that video first. So Orange says that putting it on standby will save you tube life, according to the designers themselves on YouTube. Sweetwater, however, has published an article that says that, oh wait, this is an antiquated practice, kind of like what we talked about before, and it actually says that it will hurt the tube, in the long run, right? And then it says that the notion that it will protect the tubes is false, that it'll actually just protect the capacitors. That's according to them. So we kind of don't know who to believe. So I did my research on this. So first, let's see if we can demonstrate it. All right. So of course, we're not going to hear it when we go from standby to 7. Yesterday, when I went back to standby, right, it was a loud pop. I'm just going to play something silly for about a minute. Let's see if we can reproduce it. If we can't, oh well. Okay, here we go. You should hear a pop. Okay, it wasn't there. All right, so yesterday it was there. Okay, let's try one more time. Okay, now we're in the 15 watt mode. I mean, it's a loud pop, dude. Not playing anything because I don't like just making up stuff. If you want to hear my riffs, check out the song below, the Hill God Band. I will post it as a link. Okay. So let's see. There we go. That's a loud pop. You heard it, right? Okay. So, for the rest of the discussion, I'm just going to put it in 7 because it's better to put it in 7 than put it on standby. Like I said, according to Sweetwater, these two sources basically contradict each other. The orange amp makers and Sweetwater. All right, so you heard it. That's pretty loud, right? So we talked about this yesterday where it's actually, I said that it's actually like, what people are suspecting is that, well, anyway, we started with the transient current, right? So there's transient currents there, and then that's actually causing an arc. So we talked about all of this in the last video, right? It's actually causing an arc, kind of like when you have 2 points and then the electricity actually jumps from one to another, right? It actually basically, finds a path, right? Much like lightning. And then that's what you're hearing here. So what I've done is I basically sort of worked out the math and everything, and did my research as well. So here's what I found. So we'll go from top to bottom. This is like my EE exam. This would be like EE 101. This would be like one problem. All right. So anyway, so here's a switch. It's a 3-way toggle. I'll try to not to get it to glare here. Okay. So it's a 3-way toggle switch. So the top is 15 watt. Bottom is 7 watt. We're focusing on this section here, right? And then standby. So contradictory to what I said before, because I was just repeating what Orange said in their video. So what I found out is on standby, supposedly the orange amp goes to 0 volts, whereas they actually said it's reduced voltage. So I guess technically that's correct, but it's actually 0 volts. So when you're in 15 watts, the power is, some of this is like the power railing and stuff, right? So when the tube is functional, it can go up to 320 volts, right around there. And then the 7 watt, it can go to basically 240, right? So those are the voltages. So what's happening here is that, why do transients happen? Transients happen, like I said, we're going back to EE 101. When I took, I have a degree from San Jose State in electrical engineering. When I took the class, just the basic class, right? This would be like a basic class. In order to take that class, you have to pass calculus 1, 2, 3, and differential equations, and physics 1, 2, 3. Because physics 2 covers electricity and magnetism. Physics 1 is basically, Newtonian, right, dynamics. And then physics 3 is, like light, right, and optics. And physics 4 is nuclear physics. But in order to take this class, you have to take all those classes and take a qualifying exam. That's to take the first EE 101 class, right? Circuits 101. So in order to take a basic circuits class, you have to pass a basic circuits exam. That's how hard the program is in San Jose State, right? So I passed all that stuff, got my degree, and there's no job. So you know how I feel about that. And now I do AI. So anyway, so don't do EE. Hardware is a dead end. Unless you really, really love it, right? You really like doing this kind of shit, right? So anyway, that's the key information that we found, is that it actually goes to 0 volts. So why do transients happen is that when you're dealing with something like 320 volts, right? And then you basically, you switch that off. So the pop is happening when we go from 15 watt mode to standby, or 7 watt to standby, right? So when you basically abruptly, right, cut that off, what happens, just think about it. Just, you don't have to be an engineer to, figure this out, but so 320 volts, you're cutting that off abruptly. So there's going to be some transients and settling time. Okay, think about it that way. It won't just cut off and then shut off and that's it, right? So there's usually, it falls off, right? It falls off. So what's happening here, let's move to the second block here. So the capacitor, remember I told you yesterday, is that discharging, right? So the capacitor is discharging, okay? It's right there. So the capacitor discharges, and it's holding like 320 volts or or so, right? So what this does is that, so here's the key here. So what this does, so why is this happening is that I knew this from the beginning, right? But I mean, of course, you have to understand, because they don't teach us how to design something like this, because this is antiquated technology. All they teach us how to do in college is to design this thing, right? To design the phone. So we don't deal with stuff like this because this is inefficient. Vacuum tubes are inefficient. Nobody learns. I mean, if you got your electrical engineering degree in 1950, they probably taught you vacuum tubes, right? So anyway, that's a whole different thing. You usually learn how to build amps like this from people who built them before, like Leo Fender or something like that. It's it's like a secret society, right? Or you learn it from like a one-off book or something like that, right? So anyway, capacitors are discharging, right? Capacitors hold charge, and then what happens in the output transformers is that there's obviously there's an inductor there, right? Anytime there's a coil of wire, there's an inductor. So when you turn the switch from basically off and it's going to 0 volts, remember, going back here, it's going to 0 volts, right? This causes transients. I remember my professor saying, I can hear his voice in my head, is that inductors oppose change in current. So what's happening is that it's inducing like a kickback, right, transient current, which in turn causes a voltage spike. So here's what I've said here is a right, coil of wire, right? Coil of wire is an inductor. And then, so that causes a voltage spike, right? That causes a voltage spike to negative infinity. Now, if we do some calculus here, so the equation that governs that, like I said, I remember all this from, EE. And of course, I had to do some research too, because it's like, I haven't done EE in a while. So it's like, as I did this, it was all coming back to me. It's like, oh yeah, that's right. I remember, Professor Moriarty saying that, V equals L di dt, right? So that is the equation for voltage across an inductor. L is the inductance value and di dt, right? And the current across the capacitor is C dV dt. We used to make a joke about that. It's like, anyway, here we're going to talk about the, inductance, right? So voltage across an inductor, L stands for inductor. Inductor is a coil of wire, right? Which is in the, the output transformer, among many other places there. So I think this is coming from the output transformer. So at least that's the theory here. So VL, voltage across a inductor, is, you see, I'm getting excited about this because this is the only place where I can flex my engineering muscles, because nobody gave me a damn job. I know it's sad, but I don't want to get into it. See, I'm already getting worked up, right? I don't want to get into it, I don't want to say anything stupid. So anyway, is L di dt, right? So you need calculus to understand this. I don't want to bore you with what di dt means. So what di dt means is that it's a derivative of current with respect to time. I is for current. So if you take the limit of that right there, it goes to negative infinity. So the negative sign is the kickback. So it's in the reverse direction, right? So it's in the reverse direction. So that tells us that basically what it is it tells you that, it creates a, right, a voltage spike, which is what we're hearing. And then, so I'll basically summarize it right here. Okay? So it is an inductive, what did I say here? I can't read my own writing. Oh yeah, inductive transient current kickback, which causes a voltage spike. Okay? Inductive transient current kickback. Kickback is in the negative infinity, right? So that's where we get the negative sign from. I mean, that tells us that it's a kickback, right? Right, which causes a voltage spike. So it's kind of like a short burst of voltage, which is caused by transient current. So that's what's causing it. And to sum this up again, when you abruptly turn something off, this causes it. So, right, when you go from 320 volts and then you abruptly cut that off. So there has to be safeguards here, because this is basically kind of like a power supply noise. This is why I said I knew immediately when I heard something like that, I said, oh, capacitor will take care of it. So after some research, that is the solution there. So I will talk about that towards the end of the video. So that's basically what's going on here. So we can attribute this to poor design, right? Poor amp design, and then also poor quality control. Now, sometimes I say some stuff, but don't take it the wrong way, right? I said basically yesterday, oh, this is made in China, so the quality control is poor. China is actually beating us in the technology race. They're building like, killer, AI-based, robots. And we're building like, friendly robots, right? They're building already there. So they're going to win the technology race because, I took what did I take? I took a mid-level management course at Santa Clara University. It was a graduate course, right? Because after I did my EE, the next thing to do was like get some kind of, right? Take some business classes and stuff like that. I just thought it would be good. So I took that class. And we had this instructor, and when you have like old, I'm joking here, right? When you have like old white instructors, right? They have like a wealth of knowledge. So this guy was like, he lived through the 60s and 70s, and he used to tell us, the 60s and 70s, the aesthetic in America was that if it was made in Japan, right, it was a piece of crap. His exact words, right? It was a piece of crap. Any toy, anything made in Japan was a piece of crap because they didn't know how to manufacture things. Right? They didn't know about quality control. They didn't know how to manufacture things. There's a whole science about how to, basically manufacture and then, get things ready for production and assembly and then roll things out like that. So what we did here was that we sent our best guys over there. This is crucial, right? We sent our best guys over there because people started outsourcing this stuff because it was cheaper to do stuff in China, right? So, of course, now it's completely outsourced. But in the beginning, it was like a few things. Whatever it was. Maybe it wasn't electronics. Maybe it was something else, right? So these kind of things were outsourced to basically Asia. So we had to send our best guys here. Sometimes like military trained, sometimes like, right? Top, QC engineers, top engineers, design engineers over there and teach them how to do risk management. So we taught China, we taught Japan, we taught those countries how to build a production line, how to build an assembly line, because we outsourced our, things over there. And then we wanted to make sure that when we get them back, they're, good quality control. So we basically gave all of our secrets away, how to manufacture things, what is the knowledge, the core knowledge, right? Now, after 50 some years, right, or more, now they're ready to basically overtake us and beat us at our own game. Hence my point that, they're winning the technology race. In 50 years, they would have won the race because we outsourced everything. Anyway, so when I say things like that, poor quality control, take that with a grain of salt. Anyway, so story time, right? Anyway, so they should have caught this. According to this label up here, which I still haven't taken off, 2 inspectors have basically, QC'd this label right here, right? 2 QC managers, have okayed this. So they should have caught this popping noise and then sent it back to design and be like, wait, why is it, causing a popping noise? So that loop was never closed. So now I have to deal with it, right? So we defined everything. In summary, we defined why it's happening. It's happening because when you switch voltages, high voltages off, it's not just going to stop abruptly, right? It's going to fall off. And when it does that, when you're dealing with, high voltages like this, sometimes it can, have transients. That's why it's not happening all the time. Notice that it's not happening all the time. So you may ask, well, why is that? Well, that's because, I don't want to get into the whole theory of it, but that's the sort of the randomness of it, right? That is the randomness of it, where sometimes certain favorable conditions exist where the transients are diminished before we, actually hear them, right? Sometimes they're suppressed naturally, right? Depends on the AC cycle of when, you turn it off, right? So sometimes it's suppressed naturally. Now, if we turn it off when the amp is in an unfavorable state, right? That's when we get the pop. So it's kind of random to where uh, it can happen whenever. It basically depends on the exact time where I turn the switch on and off. If it's a favorable condition, the transients will diminish by themselves. If not, it'll pop. So maybe this was a hidden thing that nobody discovered, right? So anyway, like I said, when I first heard this, I immediately knew that, okay, this sounds like, where have I heard this before? Well, power supply, right? When you supply any electronics with power, the power has to be clean. Sometimes there's like crackling and things like that, right? Sometimes there's like, spikes in the power supply that can damage your equipment. This is exactly what happened to the two other orange amps that I had. Remember where the right the cable, the power cable on the back, didn't securely fit. So when I wiggled it, it caused basically a power spike, and it was exactly like that, this exact noise, right? So the first time this happened, after about an hour of me playing, I thought the amp was dead. I was like, all right, great, I just killed another amp, because it was the same noise. But luckily the amp still worked. This is a different issue. This is sort of a front end issue. That was more of a powering the entire circuit board issue. So same sort of thing where when you have spikes like that, right? Basic power supply design is you have to have a clean power supply. So that's why they use capacitors to get rid of power supply noise. So when I heard that kind of that spike, I immediately knew, oh, someone forgot to put a capacitor in there where it mattered. So after I did some research, I found out that basically what I'm going to do at some point is open this up, and then this toggle switch, what we want to do is we just want to install a small, I'll talk about that in the next video, right? Some passive components, capacitor is one of them, right? So that it catches this transient and then basically just, it's not going to let it through, right? It's a filter circuit. So we're just going to put a filter circuit here. So if I do it, so now that I understand it and it doesn't really hurt the tube, right? I'm not going to do it right now because it's just, because it's more of an ordeal. So remember that these things have, like I said, 400 volts in them, and the capacitors that hold this huge amount of voltage, like the older amps, what they do is the charge can be in there for like weeks or days or weeks, right? It may not drain instantly. Modern amps, however, they force the capacitors to drain right away, supposedly, but you can never be sure. So the first thing you have to do, you have to open this up, and then you have to basically test it with a multimeter, right? And I haven't had a multimeter in like, like a multimeter voltage meter, right? I haven't had one of those since, San Jose State EE laboratory. I probably have one in my garage, but where do you find it now? With all the boxes, I don't know where it is. So I probably have to buy another one. So it's going to take a little bit of time, because you don't want to go in there. Of course, like I said, they've built a drain circuit that drains the capacitor supposedly right after you turn it off, right? Within a few minutes or so. But you never know. So there's a possibility that some of it, didn't get discharged when you turn it off. Remember I was saying when you're, basically going to zero, when you're putting in standby, remember yesterday I was saying it's discharging, right? So it completely discharges when you turn it off. So the other kind of weird thing is that putting it on standby is essentially the same thing as putting it in off, because it only, it's zero voltage. However, the vacuum tube, right, is kind of kept warm with like 6 volts or something like that, which is what I found out. So that's the whole thing in standby. It's not a lower voltage. It's basically 0 volts, but they just sort of keep it warm for you. So they just keep the vacuum tube warm. So if you look in the back, it might still be kind of, glowing a little bit, right? It just kind of warms it up, and that's supposedly it. But like Sweetwater has said, in modern, interpretation of this is that it's basically going to, reduce the tube life. So, in summary, this is what we're going to do. Okay? In summary, what we're going to do is that we're not really going to put it on standby. And then when it's in 7 watts or 15 watts, we can just turn it off because, for example, this amp doesn't have a standby. This amp costs more than, right? This amp doesn't have a standby. So a lot of amps don't have standbys. So we don't need to do that. Till even if I put that filter circuit in there, right? According to sort of the modern updated philosophy, it's going to basically kill if you leave it on standby too long, it's basically going to, in the long run, it's going to affect the tube life in a negative way. So you don't want to leave it on standby for more than 2 minutes or so. So it may not even be worth it for me to go in there, like I said, buy a, multimeter. I mean, a multimeter only costs like $10, but I'm just saying, right? Go in there and then you risk the, if it hasn't discharged completely, right? High voltage can basically arc, right? If I'm going in there doing shit, it could basically arc. So, I have to basically, be completely sure. Because this is not solid state. You could basically discharge 400 volts across your chest, right? And die. So, unless it's absolutely necessary, and you can't do it from the outside. So I'll have to open it up, go in there, and basically put a filter circuit right around the, right, this toggle switch. Others have done this in a different kind of way. They have other workarounds and stuff like that. Of course, if you do that, you'll avoid the warranty immediately. So if it's not required, if I'm not going to use standby anyway, I might not use it, right? I might not do it. So anyway, that's the summary is that standby just goes to 0 volts. It's basically the same thing as turning it off, except it keeps the vacuum tube filaments kind of warm. And it supplies it with around 6 volts or something like that or something, right? I didn't read too much deep into it, so that part of what it actually does. You have to basically look to see how they built this thing, right? So... So the only thing here is when you go from, like right now I'm at 7, I want to go to 15. So don't put it on standby and then go to 15. So you're going to have to just throw it in one swoop. I don't even know if that's possible. Let me try it. Let me go all the way to the top real quick. See? It's going to do it. It's going to pop. Because it's going to, momentarily go into the standby. So it kind of sucks. So you're only affected if, for example, in the middle of practice, you're going to go from 7 watts to 15 watts. There's no way to avoid that pop if the pop happens, right? If you catch it when it's not supposed to happen, then you're okay. So, and as I told you, I can turn down the volume on the guitar, I can turn down the volume on the amp, and it'll still happen. Right? This was actually, let me see. See? You can still hear it. So anyway, that's the thing. It's kind of universal. It's just basically poor design. And I suspect, other amps will probably have it. So, now that I sort of tried to go from 7 watts straight to 15 and it still did it, I almost have to put that circuit in there. So I will cover that in another video, probably not anytime soon. So the way I think that we can work on this is that just leave it, start it when you turn the amp on, leave it on standby for about 2 minutes. And then just take it off standby. And then, whether it's going to be 7 watts or 15 watts, just leave it there and then turn it off. So you don't want to switch back and forth in the middle of playing. So if I were to play with a band or something, I would just put this in 15 watts and that's it. So I don't have to worry about it. The only time I have to worry about it is if I go to standby and such. So you never hear the pop when you go from standby to 15 or standby to 7. It only happens, which makes a lot of sense, right? Because standby is 0 volts. So you don't get the pop when you go from 0 volts to 320. You only get the pop when you go from 320 down to 0 because you're turning the circuit off. So, like I said, I'm not going to cover the circuit now. Probably, that's something that I might do in the future at some point. Anyway, that's the update. And then to summarize what that comment I made in the last video, the comment that I posted is that Orange seems to think that this saves tube life. Sweetwater thinks a modern approach is basically, it's going to kill the, it's going to destroy the tubes in the long run. So, I don't know. And like I said before, it's a kind of an antiquated feature. So you're not going to do anything if, like, for example, I'm at 7 watt right now. I can just turn it off. I don't need to go to standby. Right? Maybe standby might be good just when you warm up the amp when you first start it. And you don't get the pop there anyway. You only get it when, like if I go from here to standby, I'll get it, right? So when you turn it off, just turn it off, I guess. I don't know. And I also found out that returning this, since this is like $800, right? It's $864 out the door with tax, is not that easy. It's sold by somebody else. So for me to get my money back, they said it would take like 30 days because Amazon would take it, ship it to whoever, had it, and they don't have any more. This was the last one, so they can't just send me a new one. Right? So it would take 30 days for them to take it back and then verify it, make sure that, right, it's not damaged, make sure it's not, for them to give me back the money. I don't want to buy another amp when I don't have the money returned to me that I've already spent. So returning this is not going to be easy. So that's pretty much it. This is the second video. I'm not going to talk about this anymore. So in this video, we pretty much covered it, why this happens. It happens because transient currents induce a voltage spike, and it's kind of a kickback from the output transformer.